So I'm going to explain a little bit about question 7 and probably question 8, just because this is kind of interesting. So here are some things that, in fact, you should know. You should know the expansion for certain functions, like e to the x is a really amazingly simple expansion. So e to the x is 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial, right? And so on and so on and so on. So notice it's not alternating. Everything is positive. And in fact, I could write this. I'm going to start with n is equal to 0. I'm going to go to infinity. So if I had infinitely many terms, let's see, this would be 1 over n factorial, and would have x to the n, right? So there's the expansion for e to the x. The other thing you know is that cosine x and sine x are also beautifully symmetric. Cosine of x is going to start with 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. Right, this is going to keep on going. Notice that this is alternating. I'm going to start with n is equal to 0 also. Go to infinity. This is going to be negative 1 to the n. Right, this is the 0th term, so this is the first term. That's the third. This is where n is 1, so I'm going to have x to the 2n over 2n factorial. And that's something you should know. And you also know sine x is another interesting expansion. We have x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, right, blah, blah, blah. I'll also, just for the heck of it, start with n is equal to 0, although I don't have to. And this is going to be, so this is the 0th term, so I'm still going to have negative 1 to the n. I'm going to have x to the, let's see, this is the first term, this is the second term, so x to the 2n plus 1 over 2n plus 1 factorial. Okay, and it's also noteworthy to note that the derivative of sine, so x to the 2n plus 1, is cosine, x to the 2n, so that kind of works nicely. Okay, let's talk about question 6, right? So for question 6, I'm asking you for e to the ix. And you have discovered that all you need to do is plug in whatever we have here is kind of a stand-in for x. So I know that this then is going to be 1 plus ix squared over 2 factorial plus ix cubed over 3 factorial plus ix to the fourth over 4 factorial, right? And we can keep on going. And I could write that in sigma notation. I'm going to simplify this a little bit. This is 1 plus ix. We know I squared is negative 1. So that becomes negative x squared over 2 factorial. I to the third is negative I. So this is going to become minus I times x to the third over 3 factorial. I to the fourth is just 1, so that's x to the fourth over 4 factorial. And then we'd keep on going. Okay, so that's that. Now, the next thing I asked you to do for question 7. Question 7, I asked you to find an approximation for f of x equals cosine of x plus I times the sine of x. Cosine of x plus I times the sine of x. Now, cosine x, we know, is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial plus blah, blah, blah. And I'm going to multiply everything in sine by I, because I can do that. So that's going to give me ix minus ix to the third over 3 factorial plus ix to the fifth over 5 factorial minus ix to the seventh over 7 factorial, right, plus blah, blah, blah. And now I want to clean this up a little bit. And here's what I would like to do. I'm going to put this in order. So I'm going to have 1, my linear term is ix. My squared term is negative x squared over 2 factorial. My cubic term is negative ix to the third over 3 factorial. Then I'm going to have x to the fourth over 4 factorial. And you can see what is going on right now. What you should be noticing is that this is exactly what we got for question 6. So that if we have cosine of x plus I times the sine of x, that should be equal to e to the ix. So you could do something like this. You could let x be, well, let's let x be pi over 2. So cosine of pi over 2 plus I times the sine of pi over 2 should be equal to e to the pi over 2 times I, which gets a little crazy. We know cosine pi over 2 is 0, sine of pi over 2 is I, equals e to the pi over 2I. But let's do this. Let's let x be equal to pi. So this equation becomes cosine of pi plus I times the sine of pi equals e to the I times pi. Cosine of pi, in fact, is -1. Sine of pi is 0, so this gives us -1 equals e to the I pi. So e raised to an imaginary number times an irrational number equals -1, which is kind of astounding.